Okay, so today we're diving into some pretty heavy stuff. Max Born's Nobel lecture. You'd think Nobel Prize winner, he'd be all about celebrating, right?
You'd expect that, wouldn't you?
But this lecture, it's like different. It's like he's sending out a message from the front lines of a crisis,
Oh, absolutely.
when everything physicists thought they knew about the universe was just falling apart.
It's true. This takes us right back to the 1920s, a time when physics was in total upheaval. I mean, imagine centuries of this beautiful, elegant structure of classical physics, right?
Right.
Newton's laws, explaining everything, apples falling, planets orbiting, the whole shebang.
Makes sense.
And then Planck shows up and throws this massive wrench in the works, the quantum hypothesis.
Yeah, because suddenly light, which everyone was positive was a wave, is acting like a particle or something too.
It was a huge challenge. They didn't know what to do with it.
Mm.
On one hand, all this experimental data backing up Planck's idea.
Yeah.
Quantized energy, these little packets, bursts, however you want to picture it.
Okay, but at the same time,
But then on the other hand, it just completely clashed with every fundamental thing they thought they knew about physics.
so we've got these physicists staring at data that just doesn't make sense. What they do, just give up.
Huh. No, not quite. It was a time of, intense research exploration. Born actually compares it to a game.
A game.
Yeah, like they were trying to guess the rules of this new quantum game while they were playing it, trying to figure out the right moves as they went along.
So they were basically making it up as they went.
It sounds crazy, but that's often how big breakthroughs happen, right? Someone has to be brave enough to go into the unknown, try new things.
No fear.
And Born, he really credits Werner Heisenberg with being that person.
Heisenberg. What did he do that was so revolutionary?
He changed the whole approach. Instead of trying to visualize what we couldn't see, he said, focus on what we can observe. Things like the energy an atom emits or absorbs.
Instead of like trying to draw a map of a place you've never been, you just listen for sounds.
Kind of. It was a totally different way of thinking about it.
Okay. And that's what led to, all right, here it comes, the world of matrices.
Matrices.
They always sounded scary to me. Are they as bad as they sound?
No, not really. Think of it like a grid, maybe a spreadsheet. You've got numbers in rows and columns.
Okay, I can picture that.
Simple, but incredibly powerful for describing how things work in the quantum world.
Interesting. Why matrices, though? What was it about the quantum world that needed a whole new kind of math?
Well, it has to do with this really weird thing about the quantum world. Things don't always, behave the same way twice.
Really? Even if you do the exact same thing?
Exactly. And even the order you do things in can change the outcome. That just doesn't happen in our normal world.
Okay, now that is weird. How can the order you do things matter?
Hmm.
In my world, if I open a door and then walk through it, or if I just walk through the door and wish I had opened it first, well, the outcome's the same.
That's a great way to put it. You've actually hit on a huge difference between the quantum world and our everyday experience.
Mm.
In the classical physics world, you're right. Order doesn't really matter. But in the quantum world, it's a whole different ballgame. Imagine baking a cake, right?
Yeah, I like where this is going.
And adding the flour before the sugar gives you a souffle, but sugar before flour, you get a pancake. That's kind of what it's like.
Now that's just chaotic cooking. But I get what you mean. So where do matrices come in?
Well, matrices can actually handle that kind of order-dependent behavior
Right.
because it turns out in matrix math, A times B isn't always equal to B times A.
Whoa,
It
really?
was a huge realization. Like suddenly the math made sense.
It's like they discovered this whole new language and it perfectly described this new reality they were uncovering. Wild.
Yeah.
But you said earlier that not everyone was exactly thrilled by this whole quantum revolution. I mean, we're talking about throwing out centuries of scientific thought, right? What were the biggest disagreements?
Oh yeah, there was a ton of pushback. I mean, even some of the biggest names in physics, people who actually helped develop quantum theory, even they had serious doubts, like Einstein.
Oh, right. Wasn't he the one who said something like God doesn't play dice?
Exactly. He had a hard time accepting this idea of a universe that was random at its core. But it wasn't just a matter of, philosophical preference. There were real scientific and philosophical questions at stake.
Like what?
Well, it gets to the heart of how we understand reality itself. Classical physics was built on this idea of determinism, right? The initial conditions of a system, you can, in theory, predict its future perfectly, like a clock.
A cosmic clock.
Right. But quantum mechanics introduced this, randomness, this fuzziness that just didn't sit well with some physicists.
So instead of a precise prediction, you get a maybe.
More like a probably.
Like knowing exactly when your train will arrive versus sometime Tuesday.
Exactly. And it's not just that our measurements are limited. It's more like this uncertainty is built into the fabric of reality itself. Einstein and others, they thought there had to be some underlying order we were missing, some hidden variables that would make everything deterministic again.
So where did Bourne stand in all of this? Did he think there was a way to reconcile this idea of a clockwork universe with this new quantum randomness? So did Bourne think there is some way to like bring these two ideas together, this clockwork universe with this quantum roulette wheel?
It's tricky, right?
Mm.
But Bourne, he really dove into the philosophical stuff too, and he felt like, yeah, quantum mechanics raises some really big questions. But he also saw it as this opportunity, like a chance to really look at how we understand reality. One of the things he pointed out was that even in our regular world, perfect measurement, it's kind of an illusion anyway.
Wait, really? What do you mean?
Think about how we measure anything, the length of a table, the temperature, even time. There's always a limit to how accurate we can be, right?
So.
We say, okay, that table's 2 meters long, but if you could zoom in really, really close, it's not going to be perfectly 2 meters. There's always going to be some tiny bit of uncertainty no matter what we're measuring.
So you're saying this uncertainty, it's not just a quantum thing. It's always there. We just don't notice it usually.
Exactly. Born's point was quantum mechanics, it just makes us face this uncertainty head on. It's not that our world's precise and the quantum world's fuzzy. It's more like that fuzziness is just part of reality itself at every level. And quantum mechanics just makes it impossible to ignore.
Huh. Okay, so maybe instead of trying to find this perfect, predictable universe, we need to get more comfortable with the unknown, with things being, well, kind of fuzzy. But how do we even begin to wrap our heads around that?
It's a big shift, for sure. Born talks about this idea of invariance. It's like a way to understand this new reality. Imagine a sculpture. You walk around it, you see it from different angles,
Mm.
different shadows, different highlights.
Right, but it's still the same sculpture.
Yes, exactly. So the sculpture itself, that's the underlying reality.
Yeah.
And the different ways we see it, those are like our measurements.
So we're getting all these different perspectives, but they're all just glimpses of the same deeper thing.
That's the idea. Born thought. Instead of getting hung up on nailing down an exact position and momentum for a particle, which quantum mechanics says is kind of impossible anyway, we should focus on the underlying properties, these invariants that stay the same, even when our measurements change.
Focus on what doesn't change rather than what does. That's pretty deep. So after all this deep dive into Max Born's world, what's the one thing our listeners should really take away from all of this? What should they be thinking about?
I think if Born were here, he'd tell us to stay curious, to embrace the mystery. Even all these decades later, quantum mechanics is still full of surprises.
Yeah, it doesn't feel like physics has gotten any less weird.
And the deeper we go, the more we might have to kind of rethink how we make sense of the world, our whole way of thinking about it.
Be open to having our minds blown, basically.
Exactly. Who knows what incredible things we'll discover if we can do that.
It's like we're setting sail with no map, just a sense of adventure and a good pair of binoculars, hoping to see what we can find.
And with a little luck and a lot of curiosity, who knows what we might discover out there on the horizon.
Absolutely. Well, on that note, we're going to wrap up this deep dive into the very strange and very wonderful world of quantum mechanics. Thanks for joining us, and until next time, keep those minds open and those questions coming.